Hi, I'm Rafael. I'm going to talk about the efforts to bring CAS and EAS on Intel hybrid chips. So yeah, welcome. The last year was the time when we complained about things a bit. So Ricardo was talking about how it was difficult to do capacity awareness on Intel chips. I was talking about how it was difficult to create energy models for those chips. And since last year, we made some progress here. So we now can do capacity awareness is there for those chips. So we can enable CAS, and it actually works, and it does improve things in a way that we get almost the same performance and use less energy at the same time. But adding EAS is still in progress, and there are like 2 versions. I did myself, and there are other kind of attempts to do it, or something equivalent to it, which I'm going to talk about later. So yeah, work in progress. So I first would like to say a few words about how we did the capacity awareness and how it works on x86, and then what was done to actually make it work on hybrid CPUs. So this is general stuff. Performance scaling, scaling variance rather, than is about measuring the utilization of tasks in the same units, regardless of where they run. So actually, there are those 2 lines in the scheduler that are the implementation of the scaling, right? So we first scale the utilization to the maximum frequency of the given CPU, and then scale the capacity of that CPU to the maximum capacity in the system. And those 2 functions are expected to return values from 0 to scaled capacity scale, and yeah. And if you run on the fastest CPU at the maximum frequency, then there's no scaling. That's how it works. So on x86, the frequency scaling is done on is recomputed on every tick with the help of APerf and MPerf performance counters. So MPerf counts at a certain reference frequency, and APerf counts at the frequency of the CPU. And if you measure them, at the same time, the instance of time, and compare the deltas between the 2, you can figure out what frequency the CPU is running at. That's how it works. The problem with this is that this fraction may be, maybe 1, maybe less than 1, or maybe greater than 1. So it needs to be rescaled so that this function goes from 0 to scaled capacity scale. And scaling is done with the help of this additional factor here, where fmperf is the frequency of mperf, and fcap is the frequency at the highest capacity of the CPU. Basically, and last year we had a problem with computing this thing. What happened was we were not quite sure how to do it. In the meantime, we realized that there was this piece of information available in the Intel P-State driver, and it tells us how to convert HWP performance units, which are some abstract scale, let's just say, to the frequency of the CPU in kilohertz. And that is just the information about the amperf frequency that can be retrieved from a model-specific register called MSR platform info, and then process somehow, and then you get the frequency, amper frequency in kilohertz as well. So if you divide those numbers one by the other, then you get this factor. And now that piece of information can be also derived from CPPC data, but it depends on the platform firmware. Because the nominal freq and CPP and nominal perf in CPPC are just integer numbers, which means that the OEM provides them, and OEMs may or may not want to provide accurate numbers and may want to tweak them somehow for value add or similar. And so so recently we have been promised that those things will always be, we always come from Intel reference BIOS, and they will be truth and only truth, and so on, and help them get. So, but for some platforms, we still have those numbers encoded hard coded in the driver. So not those, but just the scaling of CPU as a single number. But in principle, you can use CPPC to get that, and then this is the formula. And then when you compute it, you can put it here. And this is all simplified, by the way, because the way the computation goes, it has to avoid like rounding errors and things like that. So, but overall, this is okay. So. The key observation here is actually there are a few of them, and one of importance is that HWP is the only way to get the information about the full capacity of a CPU on some hybrid platforms, because there are no other registers where you can get that information from. The next thing is Intel P-State has all information that's needed for computing this, what's needed, so that. And it knows about HWP because it's the driver for it. It knows how to compute this because it needs it already for implementing this interface in CPU freq SysFS, which is in terms of frequency. So anyway, you need to cast the HWP scale to the frequency scale, and so this is known anyway. And CPPC is used by it, so Intel P-State can just compute this thing and tell the scheduler use it, and then it all works. The quite important thing is that this only has to be changed when the highest performance of the CPU changes, which can happen sometimes, but not very often. And actually, on the platforms that I have seen, it doesn't change. But it is possible. So the architecture allows that to change. And then when it changes, the Intel P-State receives notifications about it, and so it can recompute everything and again reconfigure the frequency scaling code to use the new values. Okay, and then so this was about the previous slides were about frequency scaling. Now the capacity scaling is straightforward if you do it the way I said. So then the observation is that the HWP is the performance levels are in the same units for all CPUs in the system. And that actually is an architectural decision. So And because it is in the same units, you can just take, the highest performance of one CPU and the highest performance of the other CPU, divide them by one by the other, and then you get the scaling factor, like here. So we get the maximum highest performance of all CPUs, and then we use that to scale everyone's performance, and then that's it. Yeah, so we get all the information we need from HWP and from Intel P-State in the form of the scaling CPU, and then we can compute all of that and use it. This is done only for the SoCs where there are no SMT cores. So SMT is still a problem, and it's going to remain a problem. So wherever we have an SMT core, we just use the previous approach, which is to run everything on the cores or CPUs with the highest performance, and then overflow to other cores or CPUs. Okay. All right, so that's done. But we still have EAS or equivalent to implement. So the problem is that capacity-aware scheduling allows us to move big tasks or high utilization tasks, I should say, from smaller cores to the bigger cores. But then we need a complementary mechanism that will move low utilization tasks from big cores to small cores, so we can say vacate all the big cores if there's not too much going on in the system, and that could be EAS, that could be something else, but that's what we need essentially. Oh, I should probably say that on Intel chips, the small cores are the performance difference between big cores and small cores is not huge. So at the same frequency, in modern SoCs, it's like 15% of a difference. Small cores are really much smaller because it's like 4 of them take the same chip real estate as one big core, but that includes cache, which is the most, I would say, chip real estate consuming piece of it, because so that it's like the L2 cache is shared by 4 small cores in a module, and a big core has a L2 cache for itself. So that's how it goes. So that's mostly why they are smaller, but they are simpler. So, but the performance at the same frequency is really not that much different between them. But still, the smaller cores are generally more energy efficient, and that's why we want to use them first, and then overflow to big if there is no spare capacity there. All right, so first, when I started to think about enabling EAS, then there are expectations, right? Where the EAS needs to have CAS enabled, and then the energy model needs to be provided. So obviously, I couldn't get a real energy model because I don't have information, to create it, and even if I had that information, it would be still difficult. So last year I was told that, yeah, you could use a fake energy model for this, meaning artificial, and I started to wonder how to do it, and then again, I got a hint to look at the CPPC driver. I did that, and then I realized that this is not what I wanted, and started to think about how to do it again. So I looked at the energy model code and tried to try to fit into it, kind of, right? Like provide something that it will accept. Okay. And and one of the requirements is that the schedule is required by the energy model, by the EAS now, which I'm not sure about really. So currently I just, tweak it somehow so it will accept something different, but not that much different from Schedule 2. So on the regular governor part, Schedule 2 is still required, but I'm not sure if this requirement is useful. Opinions?
It really is useful for us, especially because we have overlapping curves on the CPUs, right? If you don't, that's fine. But for us, for example, a little CPU at the higher OPPs might be.
Yeah, but my point is mostly like, okay, so for best results, you have to use the Schedule 2, right? That's clear. Like for best results, but what if you? It will still work. It may not be. It may not be like super accurate or something like that, but it will still work. So I'm not sure. So I'm now changing this code a bit, but maybe I should just remove it, like those checks. Like, what do you think?
I'm fine.
So how would you calculate the energy without controlling the OPP precisely? Like, don't you need to know?
I don't.
Take that from the software.
Schedule is useful because the goal is to know at which OPP you will run. So what
right.
cost.
So I'm not saying it is not useful. It is useful for best results, but why it is required?
But because otherwise, the energy model calculation is just quite random.
I wouldn't say wrong. It may be inaccurate.
It's required because we don't want to deal with random people doing random other things.
Like what?
We just don't want to deal with people trying to use EAS and on demand.
Yeah, okay, so I guess your point is that this would be supporting those people would not be useful, right? Yeah. If they reported like a problem with it. Like, fair enough. Okay. But I need to change it just to be able to use it with Intel P-State and without Schedule 2, because that's not that much different, and I don't think there is a problem with it. But so okay, fair enough.
Yeah, that would be why you don't want to use Schedule 2, even if it's not really useful.
Because Intel P-State doesn't use a governor at all. Like a regular governor, it just has it like in. It uses the governor that's implemented in the firmware. So that's why, right? And I just don't want to use any governor in it, or maybe give people an option to use a hardware governor versus Schedule 2.
Can we set a target frequency request?
Yeah, we can.
And then totally ignore.
No, so there are pros for doing this. Like, for example, if you use Schedule 2, then you can take utilization clumping into account, whereas otherwise you can't. But that's the only difference between Intel P-State governor and the Schedule 2 on Intel, right? So, yeah, if somebody wants to use just the hardware governor, I have no problems.
Just to clarify, because you are using essentially the Schedule calculation of which OPP we will be using. It doesn't matter your fake energy model.
Yeah.
But you're using the calculation anyway, even though Schedule will be used for actually deciding the OPP. But you say it reasonably matches what Intel P-State issue.
Yeah, it's the same calculation basically, but based on internal utilization metrics rather than on PELT. right? But that's pretty much the same thing. So we measure utilization on those.
Can you actually predict what HWP is about to do? Like,
yeah.
And then you
yeah, so I don't have those graphs here, but if you plot, so we do plots like real work versus the performance level, the HWP. So we try to run an increasing amount of work. It increases in every step of the calculation by a certain percentage, and then we plot that against the frequency, and it turns out to be linear. So it responds like linearly to increasing work. So that's basically, what we assume anyway in the scheduler.
Give or take thermals and all that, like it could decide to do something.
Yeah, it could, but then it's still linear accepted. So the problem is that they may chop off some pieces of the curve, but the section that still remains is the same. Like, so they may not decide to go above a certain frequency, or may decide to not go below a certain frequency in it, but they are still on the energy efficiency curve, and then then it responds linearly to performance, except for the ants.
Right.
So it's predictable, basically, right? But there are, so if you run on a single CPU, that is. Because otherwise, when you start to get interactions between all of them, caches and everything, then it gets much more complicated, and then you can't be predicted. But as long as you run on a single CPU, yeah, you can say, yeah, that's linear. Okay, so there are a few things that I maybe, yeah, it's worth mentioning. So the slides are mostly for myself to remind me about certain things I wanted to say. So first of all, if you take the energy model as a fake one, then it really doesn't have to do anything with energy. It is just a parameterization of the scheduler, kind of, because then you can put whatever numbers you want in there, and even such numbers that will then cause the scheduler to prefer your big CPUs rather than small CPUs. But still there are limitations of it. But basically, you can just use it as a way to parameterize what the scheduler does. However, whatever you do, then each perf domain that you define in the energy model is regarded as a voltage frequency coordination domain today. So the assumption is that if you change the frequency of one CPU in this domain, that it will also change for all of the CPUs in it, and the same for voltage. So the energy can be computed as the sum of the utilization times the cost for this. That's why. And all CPUs are expected to be identical. So for me, this was a problem, because there is a concept of favored core on Intel chips, and those favored core are basically look exactly the same as the other cores of the same type, except that they can turbo up to higher frequencies. So this was not very convenient, but okay. And also, I would prefer that energy models to be at least as long as they are fake, to be in abstract units, and then it's so that whatever is there in the energy model is not directly compared to utilization, maybe with some scaling or something like that applied. But that again, because I will talk about this, why this is problematic in a couple of minutes. Maybe I'll skip this. It's in the slides if you will this like some, observations about the implementation, maybe not really interesting here. Okay, and the problem with comparing the data in perfect domains directly to utilization is that they need to be updated on capacity changes every time. And that's, again, depends on what really changes, but if your highest CPU, the most performant CPU's capacity changes, then you need to recompute everything for the entire system, because then you need to rescale things and so on. So if that can be avoided.
But this is, when I see your V3 code, it actually saves you on your platform, right? Because HWP is not ready when the scheduling comes up the first time.
No.
And then I think it's the third time.
Yeah. So it's not ready. So
this interface saves you to, to reload or to load the energy model once you have the HWP.
Oh yeah, you can. Right. So yes. So that's how initialization works. But then on every change, like if the if the capacity of the most performant CPU changes very often, then you need to do all of that every time. Like recompute all the entire energy model.
Does this actually change frequently?
Not today, but there is nothing to to prevent it from changing. Like for example, you would need like a thermal envelope of some like a thin laptop without fans. Then you might need to clamp it occasionally from the firmware, yeah. And then in that case, you need to recompute everything every time, going back and forth, right? If you
we can throttle it. If it changes too often, it's not useful either.
Yeah, that's true. So anyway, what I'm saying is that it will be more convenient if it didn't have to be done, right?
For the thermal mitigation, you don't really need to take the per domain. You just have to say that the current max compute capacity is this value. And EAS try to go above.
Yeah, but then you need to recompute. That's what I'm saying. You need to recompute the state tables.
If you initialize the state tables from the start, then you could just disable the top or like you don't have to do an actual accurate hardware representation. You can just initialize like 5 OPPs arbitrarily and disable the top 4 if you run into arbitrary throttling points. Yeah,
what I'm saying is that the hardware tells me that my highest, highest HWP highest perf has changed. And whatever the reason, in this case,
you don't know the steps of how many.
I know how many levels there are, but I don't know upfront, how much it will change, and also it may change it may grow and not, decrease.
Maybe I'm missing something. How many? In your energy model, how many OPP do you have?
Actually, right now there's 4.
Okay.
Per CPU, but not in this. Okay, so there are. Actually, I should probably go.
Yeah. Go ahead. That, you can say now my max compute capacity is this value, even if the value is in between 2 OPP. Right now we don't care. It's just that we'll never ask for more than this value, and then we'll fall back to the first OPP.
Yeah. But so again, it can change both ways, so it can grow as well. So if it grows, then
okay. Yeah. If it grows, then
yeah.
But that's something I'm not sure that it's a real problem if we go above 1024. To be honest.
Yeah. So this is something I just noticed, right? That I need to do this because of that, and if that is not there, then I might not need to. But so we need to talk about the details.
No, right? Like it cannot grow indefinitely.
Right, yes.
wants to.
Fair enough. Yeah. Yeah. Okay. So there are two ways in which I try to implement EAS. One way is to use to create a perf domain for CPU type. So we have, like, in a simple case, which is not unheard of, we have two CPU types in an SoC, big and small and big, or E core, P core, or whatever. And then the small is assumed to be more energy efficient than the big. And it is always more energy efficient, so no crossover points, no nothing like that. We don't need to worry about all those things. So it's very simple. If the capacity is sufficient on the small cores, we want to run there. If it is not sufficient, we want to overflow. Then when it becomes sufficient again, we want to move everything back to them, and so on. Okay, so the simplest thing that came to my mind was to just create a perf domain per CPU type with just one OPP, and that OPP will just represent the cost of running on either small or big CPU, right, depending, and put all the small cores into one domain, all the big cores into the other domain. Off you go. So this is this will take you to the patches. So I decided to use, the barcodes, because everybody does this nowadays. But anyway, yeah.
You're creating a perf domain per CPU type, but is there a relation between the frequency of each CPU? How you choose the frequency between the two CPU at the same time?
So that's where the governor part goes in. So this is decided by the firmware on the processor, like what CPU to run it.
The firmware, is it taking into account the fact? Is it making decision on the little cluster, let's say, or is it going to make a decision among the whole platform, or what is it?
No, so if you have to place tasks on CPUs, and then when there is something is running, then the utilization is computed by the firmware, and it adjusts the frequency to the utilization.
I think what you're asking is there's still like a shared rail, so the entire process.
Yeah, okay. If there's coordination, yes, there is. So big cores usually have their own voltage regulators each, so they can run at completely different frequencies. The small cores are coordinated in modules of 4. So again, the different modules have different voltage regulators and can run at different frequencies, but within the same module, they are coordinated. But the CPU interface is per CPU at the same time, because HWP is per CPU. So that's another kind of like, okay, fine. This is kind of not in agreement with the assumptions made by the EAS, but anyway. Okay, so this is simple. So, I posted patches. There were some comments on them. Interesting thing is that in this model, you don't need to worry about updating anything. You just set a cost and forget it, essentially. And there are, well, I wouldn't say issues, but yeah, it requires some tweaks to the energy model code, because as is, it doesn't accept the type of simplicity. You need to be able to expand the perf domain, which is something that Dietmar was talking about. So if a new CPU appears after initialization, like it was offline to start with, and then we bring it online, then it needs to be added to this, perf domain that matches it, and then this is not in the API for the energy model yet, so I need to kind of extended for this use case. Favored cores are not really favored, so they are in the same bucket as the other big cores because favored cores are usually big cores. And so that's a minus. And
this is a decision you made, right? You could have a trial system.
Right. This is the decision. Yeah, but so I'm talking about this particular model. This is a drawback of it. Like, but it could be done. Like there could be 3 perf domains, something like that. Okay, and that's something that we've seen in testing of this. So first of all, we observed high migration rates between CPUs of the same type. I think the reason why is that the scheduler picks up a CPU with the highest per capacity, and then so if the tasks go to sleep and wake up, then every time a task wakes up, another CPU turns out to have the most per capacity, and it goes there. And
I mean, you normally have at least 8 little CPUs, for instance. Right?
Yeah.
Depends on your workload. If you only have 2 or 3 tasks, obviously this is happening all the time. But if there's more,
so it depends on the workload, obviously. But there are workloads in which this happens a lot. Yeah.
You said the little core share L2, right? So at least within the module. So
within a module, yes.
So the migrations, same without on all little cores, we notice that migrations would.
It should not, yeah, so in theory, yes, but if this happens between modules, then this becomes problematic because you basically leave your L2 behind.
Then you can have the same capacity and just initialize that per module.
Yeah, so you could, yes, you could. I didn't do that because then I would need to look at the cache hierarchy in the code, and then it will get complicated just because of this thing. But then really the migration doesn't really matter that much, and we don't really see that it matters a lot in the results anyway. But it's on a theoretical level, it's like, yeah, it's a possible glass jaw, right? It's like where it can go wrong. So. But we also haven't seen a lot of improvement in general workloads. So obviously you can create a synthetic workload where it does matter, but in general workloads like the bunch of benchmarks, a set of benchmarks like 400 benchmarks ran on all of this, it doesn't make a lot of a difference. Either way.
Are you measuring only performance or also energy?
Also energy, but I think that the energy was measured with the help of RAPU, yeah.
Because I mean, it was really showing I think it was 13 generations.
It really depends on benchmarks. So what is really common in the Linux world, x86 is benchmarks that utilize the full CPU. And there's barely any spare capacity.
But there are also things like video playback and stuff like that, and they should show the difference, which they don't.
I saw great improvements with your patches.
Okay. Well,
on Raptor Lake.
On Raptor Lake. Okay, so but I believe that you shared the numbers, right? So they are.
Yeah, sure.
They are somewhere in one of the responses to this patch set. Okay.
Yeah, but this is always a problem, right? Like the normal benchmarks, they don't show anything, and then you really have to put a little bit of smart into your test application.
Yeah, that's true. But on the other hand, we want to know how much of a difference this is going to make to an average user that will run unmodified stuff, right? And then,
it should show some improvement.
Yeah, so this is sort of like, maybe not super convincing, but we okay, so let me talk about the other approach, and then we...
So what do you do with the LPE cores?
LPE cores, nothing, because LPE cores are... In this model, LPE cores are regarded to be the most energy efficient, so they will start running everything, but which is wrong, by the way. because they are, yeah. So that's a whole different discussion, like what to do with them and how to do. But anyway, so you know you can tweak your fake energy model to prefer middle cores, and then big cores, and then LPE cores. that's something that can be done quite easily. And I'm not sure if we need anything else, because we have, on top of this, we also have this LPMD thing that knows more about the SOC, and it can like put LP cores in a back burner, sort of, and avoid using them entirely because. Yeah. All right. So there is this. The other approach is to use a perf domain per CPU, in line with what CPU Freak does, and in accordance with HWP, and that is the other simple option. So the idea is that still the energy model prefers small CPUs. So they have a large cost component in their perf domains related to the CPU type. And then within the perf domain, there are 4 like fake OPPs to help the load balancing between the CPUs at the same time. So this hasn't been tested yet because I posted it last week. So if you can, for example, run your tests on it and compare and let me know which one is better, then it will help. But then we still, again, I think that this is going to be tested internally, and then it will take some time because there are so many workloads to run on it, and then only then we will have some results. Okay, the pros are that this is simple for the driver. It has more control over load balancing in this case. Yeah, and it can be extended for the module thing. Like then when you know about the cache hierarchies, you can create like a per module per domain, and then it's. Say it fits EAS better than per CPU, but that's the next step, maybe, if this is promising. And then there are cons. So they something that I was talking about. So this adjusting of per domain per domains on capacity changes needs to be done, because the state tables depend on the capacity. And that's a consequence of how the energy model code is designed, and the wake-up path overhead is larger in theory. All right. So that's about the EAS. Again, the second option is more testing. And we will know if it's better or worse, and especially we are kind of hoping that the migration, the high rate migration between the CPUs of the same type will not be present in this second thing. Okay, so is the future bright for EAS on Intel? Well, maybe. Maybe not. There is one more thing that can be done in principle instead of it. So again, what we need is a way to pull low utilization tasks from big CPUs when small CPUs are available. So one way to do it is to use EAS. It works in the wake-up path mostly. I think that Vincent has patches to make it also work in the work balancer. But there is a thing called asset packing. And the way it works is it works in the idle load balance path, and it looks at priorities. So you can assign each CPU a priority, and then it will pull tasks from high priority CPUs, from low priority CPUs to high priority CPUs. And so nowadays, this is used to implement the feature called ITMT, which I don't really like this name, but anyway, because it's a marketing one, I prefer the term asset packing because this is the technical thing. Anyway, so ITMT is basically asset packing with priorities based on performance. That's what it is. So today it works by pulling tasks from small CPUs to big CPUs, but it can be made work the other way around. And
it's about like small tasks, right? So they wake up and they go to sleep. They don't have a long runtime. So
yeah.
Pick them or to move them in load balance is not as easy.
Well, so, okay. Can it made work with CAS? Yes, it can. It needs to be made capacity aware, because if it is not today. So it doesn't know about capacity. If it is made capacity aware, then it actually does work. So the adjustments are not horrible. So I've seen the patch set. It's like 5 patches in the scheduler. The majority of them are like one-liner kind of thing. And after patching the scheduler so that asset packing is capacity aware, then you can set the priorities to reflect energy efficiency, and off you go. It works in the idle load balancer, obviously, which is a shortcoming, as you said, because it doesn't, it is not efficient like a wake-up path. And especially the problem is that new tasks may be placed on big CPUs and then only pulled from them after a while, in which case it's really like we already paid for it. so it's maybe not that good. But again, this is something that can be done instead of EAS.
And like these CPUs, are they always ordered in capacity order? So CPU 0 is the big CPU, and then the littles are coming later in mass, or?
No, it may not be. It may not be. So that is still a kind of work in progress, but this is kind of as a reference. So obviously, Peter maybe not like it.
Africa, 5 minutes. 5 minutes.
5 minutes.
Yeah.
Okay, we can talk about it later. Yeah. So I'm taking this as a maintainer preference to use EAS, right?
Yeah, I mean, EAS needs work anyway, I think. So EAS was envisioned for small machines. And now we're running into 20-ish CPUs, and this is turning out to be rather large.
And growing, by the way.
Yeah, I know.
Yeah, so.
Everything is always growing. So, I mean, if we need to change the EAS, it might be a good opportunity to look at that anyway.
Okay.
I mean,
Fair enough.
Even the ARM people, they have bigger chips.
So basically, the next step here is to, again, post this test things on it and compare with the results that we get for both variants of EAS, and then.
So the key point here is what Vincent also said, that for small tasks, you really want to replace them on the way go. That's the important thing. Waiting for those others to come around and fix up.
Yeah, so that's the. Oh, sorry. Well, come on, that's this, right?
Yeah.
Oh, yeah. So, okay. So this is actually my last slide, except that the
I just have a few
references.
words on testing, because I wasn't sure what to test either. I tested YouTube video streaming and whatnot.
Mm-hmm.
Because we at ARM have a broad definition of day of use, on mobile. What does your average consumer do?
Yeah.
And maybe 12 hours of not using the app at all, just being on standby, or whatever. 4 hours of Instagram, and 1 hour of intensive gaming and whatnot. And then it just sort of, I don't know how accurate that is, but just to.
Yeah.
It's probably accurate for many people.
It's probably an underestimation, even maybe. So we can quantify how much EAS savings are.
Right.
Because, as I said, on YouTube it might be better, while most benchmarks that are generally being run on Linux is
right.
zero.
So what we see, the picture that we see internally is that we test things on say we have the set of benchmarks that we normally run, and then we draw some conclusions, that we put some code in the main line, and then the Android, the Chrome people at Intel tell us, oh, we are seeing regressions in performance, because they use different tests for evaluation, and then so this is generally not really easy to evaluate those things.
Yes, we have a similar issue. Chips are sold based on performance.
Yeah.
We're trying to.
Yeah, but that's Yeah. So why bother making a hybrid chip if you only go for performance, right? This is the question. Right. So,
people don't run with Geekbench generally.
that's true either. All right. So yeah, we are making progress with this is going to continue.
Thank you.
That's it.
Thanks.